My name is Samuel Beaulieu, and I just started a new position here at CELIA in Bordeaux, and it's also the place where I've learned this great effect, which is called photoelectron circular dichroism, that I will talk about today. So first, let me briefly outline what I will talk about today. So first, I want to tell you about what is chirality. And then I will jump to explain what is photoelectron circular dichroism. And after that, I will give you a brief historical outline of the development of this field by first showing you a lot of example of synchrotron study of photoionization of chiral molecule. And then I will talk about multiphoton ionization of such a molecule. And after this, I will show you how this is connected to our field of ultrafast science by showing you how we can use pump probe experiment to probe ultrafast dynamics in chiral molecule. And after this, I want to talk about strong field ionization and Attosecond-resolved measurement of photoelectron circular dichroism. And to conclude, I just want to give you a few brief examples how people start using this observable as an analytical tool to study the chirality of molecule in gas phase. So first, let me tell you what is chirality. So an object is chiral if it's distinguishable from its mirror image. So that means it cannot be superimposed onto it. So one of the most emblematic chiral object that we are all aware of is our hand. So our right hand is the mirror image of the left hand, but we cannot superimpose them on top of each other. So we say that this object is chiral. And chirality is not just a property of our hand, but is really a fundamental broken symmetry properties of nature. And it can emerge at any length scale. So incredibly huge astrophysical object, for example, galaxy, can be chiral due to their spiral-like shapes. And chirality can also be a broken symmetry of big man-made object. For example, this so-called Mode Gakuen spiral tower, which is located in Nagoya, Japan, is also a chiral object. And animal horns, like in the case of this impala, is also chiral. As you can see, a bit like our two hands, the impala have two horns of opposite chirality on its skull. And still going down in length scale, you can see that because of this spiral property, the snail shells are also chiral. And surprisingly, life is asymmetric, meaning that there's most of the snails are rotating, their shell are rotating clockwise, which is quite surprising. And also another everyday life object which is chiral is the screw. And the chirality of the thread has a huge impact on our everyday life in an optical lab. For example, if you want to screw a mirror mount with a clamp in the optical table, you need to rotate clockwise. And this is because of the chirality of the screw. And another very well-known now a macroscopic molecule, a macromolecule, sorry, that contains the genetic code of living organism, which is called DNA, is also chiral. And in our body and in the body of other living organism, you will always find the DNA to be right-handed. And the last example that I want to show today of chirality is this amino acid, which is the building block to form proteins, which are also chiral. So now I will stop here since today I want to talk about molecular chirality. But just let me tell you briefly that even smaller particle like subatomic particle can also be chiral. So I hope that the wide range of length scale that I've showed you of object that can be chiral convince you that chirality is ubiquitous property of matter at any length scale. So as we are interested in molecular chirality, let me tell you that a pair of chiral molecules which are mirror image of each other but not superimposable are called enantiomer, and they have basically all the same property, chemical and physical propriety, unless they interact with another object which is chiral. So for example, here on your left, you can see the plus carbon chiral molecule, which is basically giving this very peculiar smell to mint, and is chiral enantiomer, the minus carbon, it is giving the smell to dill. So with this very simple example, you can see that just by smelling these herbs, our human body is able to discriminate between these two enantiomer. We can tell easily if it's mint or dill. And here is another example of the chiral discrimination power of our body. So if we inhale the enantiomer on your left, it will act like a nasal decongestant. So if you have a cold, you use this and it fixes it. But you can, and you can buy this at any drugstore. And however, be sure not to mix it with is enantiomer, which is basically the active molecule in the drug known as crystal meth. So you can see that both enantiomers has very different property on our body. So in the last two slides, I've showed you that different chiral form of the same molecule can have very different effect on our body. And here on this slide, I want to briefly explain you, so it's not a biology conference, so it will be super simplified, but, and I also don't know much more about this, but here is a simplistic explanation about our body can discriminate between two enantiomer. So you can see that on the top, we have this right hand, which represent a chiral receptor in our body that basically receive and transduce messages from chemical messenger, which in this case will be in the analogy of this VIX and crystal meth enantiomer. And if this end is a left end, you will have this very nice and fluid handshake that you can see on the top. But if you want to handshake someone and he give you the wrong end, it leads to this awkward and very ineffective handshake, a bit like a molecule trying to enter a receptor of the wrong chirality. So the fact that our body is full of chiral chemical receptor makes him a very good machine to discriminate between the two forms of a chiral molecule. So, but however, like tasting some molecule and waiting to see the effect on our body is not the perfect way to discriminate between the two chiral molecules. So maybe as a physicist, we would like to find a more efficient way to do this in the lab. And so as seen before, a chiral molecule interacts differently when they interact with another chiral object. And so one of the chiral objects that we are aware of as optical physicists is circularly polarized light. And so we can use in the lab the interaction between circularly polarized light, which is a chiral object, with chiral molecule to try to discriminate between them. So we can use light as a so-called photonic chiral reagent. And the most widespread technique based on chiral light matter interaction is the so-called technique absorption circular dichroism, where one measure the helicity dependent photoabsorption cross-section of chiral molecule. So in this type of experiment, you see that a given molecular enantiomer will have a larger photoabsorption cross-section for a given light helicity, which lead basically to opposite circular dichroism for opposite enantiomer, as you can show on the bottom left of this slide. But as you can see here, I use the same unit as Romain was using, and also Ashley, so milliod. And you can see that this effect is very small. You measure like 4 milliod at most for this very specific molecule, and sometimes it's much worse. And the reason why this technique or this signal are so weak is because it finds its origin in the interference between electric and magnetic dipole transition, and the later one, magnetic dipole transition, being extremely weak and rendering this interferometric contrast also very weak. And the fact that this observable is so weak renders such a measurement in diluted gas phase molecular sample extremely challenging. And here comes the introduction of the effect that we want to talk about today, photoelectron circular dichroism. So in the 70s, it was theoretically predicted that if one used circularly polarized radiation with a photon energy which is larger than the IP, the ionization potential of the molecule, one can eject electron through photoelectric effect, and the angular distribution of the outgoing photoelectron emitted from an ensemble of a randomly oriented chiral molecule will be forward-backward asymmetric, while it is usually symmetric if you perform photoionization using linearly polarized light, or if you are using a non-chiral molecular target or atomic target. So indeed, in this photoelectron angular distribution, you can see that more electrons are ejected forward than backward. And to intuitively understand this fundamentally quantum process, one can use a very simple classical mechanical analogy. So, for example, photoionization of chiral molecule using circularly polarized light can be seen as rotating a nut around a thread of a screw. So in this very specific analogy, the thread represents the chiral molecular potential, while the nut represents the outgoing electron. So you can see that for a given rotation direction of the nut, it will move in a very specific direction. And for example, if you rotate clockwise, it will go forward, and anti-clockwise, it will go backward. And this is very similar to what is happening here in photoionization of chiral molecule. So before going one step further, let me just tell you that this to capture the angular distribution of this photoelectron distribution, you can decompose this in a sum of Legendre polynomial weighted by an energy-dependent coefficient, as you see in the equation in the middle of this slide. And you can see that here the summation goes up to 2n, where n is the number of absorbed photon in the process. So, for example, in single photon ionization, since n equal 1, the summation goes up to 2, meaning that the first two Legendre polynomials, so 0, 1, and 2, so the first 3 polynomials are contributing to the photoelectron angular distribution. And because the odd Legendre or Legendre polynomial are antisymmetric along the light propagation direction, it's the only one leading to this asymmetric forward-backward distribution. And so this first odd Legendre polynomial is the relevant one to capture this forward-backward asymmetry. And it's also vanishing if the distribution is symmetric, so for linearly polarized light or for non-chiral target. So if we then reverse the endedness of the light or the chirality of the molecule, this forward-backward will reverse because of basic symmetry consideration. And in our simple mechanical analogy, this would just correspond to the changing the linear displacement of the nut upon changing the direction rotation. This effect we are all aware of. And so in the lab, so the way we typically measure photoelectron circular dichroism is by measuring the photoelectron angular distribution from an ensemble of randomly oriented chiral molecule for the two different helicity, and by computing only the normalized difference, as you can see on the right of the slide. And this basically lead to such a two-dimensional PECD image. And as one can see here on the color bar, the strength of the signal is orders of magnitude larger than standard absorption circular dichroism. And the reason for that is that PECD finds its origin only in electric dipole transition. It doesn't rely on any magnetic interaction. So in opposition to absorption CD, which was relying on, as I said before, interference between electric and magnetic dipole transitions. So this is a physical reason why this signal is so strong. Okay, so now that we have defined what is PECD, I'll start a bit my historical perspective concerning the development of this field and how it came along to be interesting for Attosecond scientists. So this brings me to the first example of PECD measured experimentally, which came 25 years after its theoretical prediction. So this experiment was performed at BESI in Berlin, where people have looked at the photoionization of bromocamphor molecule using 16.2 EV photons, which are of course circularly polarized. And they were using a set of 2-electron spectrometer to place at very specific angle to extract the forward-backward asymmetry of the angular distribution at a fixed angle. And as one can see from the photoelectron spectrum on the top of the slide, top right of the slide, we can clearly see features of the HOMO orbital, which is basically located on the carbonyl moiety of bromocamphor, as well as you see the second bump, the HOMO -1 peak, which is the lone pair of the bromo group, and so on. You can see our orbital at higher binding energy. And if you look at the asymmetric part of the signal, we can see a strong binding energy dependent asymmetry, which reverse sign when switching the helicity of the light. So going from this sigma plus, sigma minus is right and left circularly polarized light. And this sign flip is the hallmark of PECD. And so directly from this very first observation back in 2001, we can see that the PECD depend on the electron binding energy, meaning that its amplitude and sign depend on which molecular orbital from which you remove an electron, which is already very interesting. And this observation of PECD at synchrotron initiated a lot of studies to understand the sensitivity of PECD to different molecular parameter or degrees of freedom. So again, this list is far from being exhaustive and complete. I'm sorry about anything which is not appearing here, but I just want to give you a brief overview of early days synchrotron studies of photoelectron circular dichroism. So in 2003, Garcia and co-worker measured the first fully angularly resolved PECD. 1 year after that, Ergenan and co-worker have demonstrated that near threshold ionization from a carbon 1s orbital, so very deeply bound electron from a spherical orbital, can also lead to photoelectron circular dichroism. And this demonstrates that the initial orbital doesn't need to be chiral, and that the scattering of the electron in the final states is also very important to the emergence of PECD, and I will come back to this later. And a bit later on, Laurent Naon and co-worker have demonstrated that PECD tend to decrease as the kinetic energy of the outgoing electron, the PECD decrease when the kinetic energy increase, and that the PECD can be enhanced close to molecular shape resonances. And later on in 2008, 2009, some group demonstrated that PECD is strongly dependent on the conformational isomer or structural isomer of some molecules. Okay, so there's a lot of more of example. Let me go quickly on these. People have also shown that PECD is sensitive to chemical substitution. For example, if you change a nitrogen atom by a fluorine atom, PECD change a lot, even if the orbital from which you remove the electron is far from this chemical substitution. People have shown that clustering can also modify strongly PECD. And also this last example, Garcia and co-worker have shown that non-Frank-Condon effect in photoionization can also lead to a sign change in the PECD. So this was quick about the history of PECD at synchrotrons, but the partial conclusion of it is that PECD is a very, very sensitive probe to investigate the static molecular structure of chiral molecule in the gas phase. And this is possible because the signal is very, very strong compared to normal or more standard chiroptical technique. So at this point of the talk, this is why I've put the logo of the conference. You might wonder, why am I talking about this? Because everything that I've talked up to now is only static experiment. And in the next few slides, I'll show you two major breakthroughs that bring PECD in the spotlight of our community. So why is it interesting for the ultrafast science community is the next topic. So one of this breakthrough is the first demonstration of photoelectron circular dichroism using ultra-short elliptically polarized XUV pulses emerging from resonant HHG in SF6 molecule. So indeed, by using very slightly elliptical driving pulse, the team here in Bordeaux have shown that XUV radiation can emerge to be highly elliptical. So the ellipticity is strongly enhanced from the driving pulse to the XUV when the harmonic are generated near the shape resonance in SF6 gas jet. And this allows people to measure PECD from a gas jet of Fenchon molecule using ultrafast pulses of XUV. And this single photon PECD measurement cover exactly the same physics that anything that I've talked about at synchrotron, but with the perspective of performing ultrafast pump probe study thanks to the very short duration of these XUV pulses. So first breakthrough that bring this topic to the attention of the field. And the second breakthrough, which actually came 2 or 3 years before the one presented on the previous slide, is the first demonstration of PECD emerging from multiphoton ionization using femtosecond visible pulses. So more specifically, Lux and co-worker have demonstrated that PECD is emerging from resonant enhanced multiphoton ionization, where basically you have two resonant photon absorption to the Rydberg states and a third photon leading to ionization. So in this case, because to come back to this equation that I've showed at the beginning, in this case, because 3 photons are involved in the ionization process, higher order Legendre polynomial can contribute to photoelectron circular dichroism, leading to much more complicated angular distribution than in the case of single photon ionization. As you can see here on the top panel, the PECD has a much more complicated angular distribution. And one of the consequences of going resonantly through a Rydberg states prior to photoionization is the pre-selection of a subgroup of molecule within the randomly oriented ensemble. So indeed, so when you go from the ground state to the Rydberg state, there's an anisotropy of the transition dipole matrix element for this optical transition, and only the molecule within the ensemble with the good initial orientation will be promoted to the Rydberg states and thus will be subject to ionization. So this will basically lead to a breaking of the sample isotropy by the so-called mechanism, which is so-called excitation anisotropic phenomena. And this is really at the heart of the complex angular distribution emerging from multi-photon resonant PECD. And so that was just briefly to explain why we see these complex angular distribution. And more importantly, these two breakthroughs, so single photon PECD using XUV out of I-harmonic sources, as well as multi-photon PECD using femtosecond visible pulse, are opening the door to very important question in our field. So the first one is, can we study ultrafast dynamics of chiral molecule using time-resolved pump probe PECD? The second one is, does PECD exist even when cranking the laser intensity and going to the above threshold ionization and strong field ionization regime? And so in the next in the next few slides, I will try to guide you through these very interesting questions. So first, let's tackle the question of ultrafast dynamics of gas phase chiral molecule. So the idea is basically to extend the static rampy PECD scheme of Lux and coworker to a pump probe scheme it's quite simple by going from one to the other. So the idea is basically to dissect the rampy process temporally by using a first linearly polarized pump pulse, which will resonantly populate Rydberg states, and using a second temporally delayed but circularly polarized pulse to measure the time-dependent photoelectron circular dichroism emerging from these Rydberg states. And you can use a lot of various wavelengths to do that, but we will focus on the most simple one, a 1+1' rampy scheme. And the way to implement this in the lab is quite simple, given the fact that you have a femtosecond laser working properly and an apparatus to measure the angular distribution of photoelectron, and that you are able to put these molecules in the gas phase. And so basically the way it works is that you record the photoelectron image for each pump probe delay, as well as for both probe laser helicity, which allows you to compute the PECD, so this forward-backward asymmetric distribution as a function of pump probe delay. So this is the way you do that. And here is a 1+1' pump probe study of the ultrafast dynamics of Fenchon. So the first demonstration of time-resolved PECD performed a few years ago. And here you can see that the time resolved photoelectron circular dichroism, as well as the decomposition into Legendre polynomial. So here you can see B0, B1, and B3 as a function of pump probe delay after the resonant population of a 3s Rydberg states of Fenchon. And so you can basically see that the B0, so the photoelectron angular distribution, and not is asymmetry or anything, just the B0, does not show any significant shift in energy as a function of pump probe delay, and decay monotonically with a roughly 3 picosecond characteristic timescale. And this evolution basically only reflects the lifetime of the 3s Rydberg states. So, but when you look at B1 and B3, you see completely different dynamics. So the B1 is decaying in 3.9 picosecond, while the B3 is decaying in roughly 1 or 1.5 picosecond. And by carefully analyzing the temporal evolution of the photoelectron circular dichroism and the different Legendre polynomial and coefficients that are forming it, it was basically shown here that PECD was sensitive to both vibronic and rotational dynamics, which cannot be seen in the B0. So it's a very sensitive probe of dynamics of chiral molecule in the gas phase. And here's another example of 1+1 prime pump probe PECD using very the same setup, same wavelength, to study the dynamics of a structural isomer of Fenchon, so which is in this case camphor. And in this case, it was shown, if you look at these B0 or the photoelectron spectrum, as well as the PECD evolution, it was shown that the PECD show an even richer angular dynamics evolution of its signal. You can see like a very complicated signal at the beginning, composed of B1 and B3, and B3 decays super fast, leading only to remaining B1 at 2 picosecond. And this is still work in progress, but one of the main conclusion is that time-resolved photoelectron circular dichroism is also a very sensitive probe of structural isomerism, even in the time domain. And this is mainly due to the different angular momentum composition of the Rydberg states, as well as different vibronic dynamics in the two enantiomer. So, we're almost done with time-resolved PECD using pump probe femtosecond scheme. But just to wrap up, so up to now, we have seen that time-resolved PECD has been only applied up to now to investigate ultrafast dynamics of highly excited Rydberg states. And one of the ongoing development of time-resolved PECD is to use XUV pulses as a probe. Indeed, because of the high photon energy, XUV is a universal probe. So it means that basically you can measure time-resolved PECD in chiral molecule excited even in their low-lying excited states using a single photon XUV photoionization. So you don't need to go through Rydberg states to be able after to photoionize using a visible or UV pulses. And this kind of setup has been developed here in Bordeaux, and which also feature a Coltrane detector. And this is in order to detect not only the photoelectron angular distribution, but also to detect in coincidence the photoion from which it originates. And so this is one of the future perspective of the kind of setup that will be used for future time-resolved PECD experiment. And using a Coltrane detector can be very helpful for PECD investigation. So static photoelectron circular dichroism has already been measured using Coltrane detector by the group which pioneered this technique in Frankfurt. And they have shown here that you can basically measure the photoelectron circular dichroism as a function of the molecular angle between molecule and light. And usually we measure PECD in a randomly oriented gas target, but here by using dissociative ionization after ionization at the oxygen K edge, and using the recoil momentum vector of the two fragments, they shown here that the PECD is strongly dependent on the relative orientation of the molecule and the light field. So as you can see here on the x-axis, you have the molecular orientation, and here's the electron emission angle. So here's the polarization plane. When you go away from this, you have maximum PECD. And if you look around the if you scan around molecular orientation angle, you can see that PECD can be enhanced, reduced, and can even switch sign for specific molecular orientation, which is very interesting. And moreover, the same group using the same molecule in the same apparatus, so the Coltrim again, I've shown that PECD is also strongly dependent on the dissociation channel, also for the case of methyloxyrin. And they suggest that the observed sign change of PECD in this case is not caused by ionization from different molecular orbital, but by effectively selecting a different oriented sub-ensemble of the molecule in the gas jet, giving rise to different fragmentation channel and thus different PECD. So the conclusion here and here are consistent with each other. Okay, so now that we have seen in detail, or not in detail, but we saw an overview about time-resolved photoelectron circular dichroism and how it can be used to probe ultrafast dynamics of gas phase molecule on very fast time scale. I would like to switch gears a bit and show you how photoelectron circular dichroism is evolving when you go from single photon ionization to RAMP and until you reach the tunneling ionization regime by cranking up the laser intensity. And I will show you that we can learn a lot of physics about ionization of chiral molecule in these different ionization regime. So here, let me put you again a slide that you saw already. And this is the first result of photoelectron circular dichroism obtained using resonant enhanced multiphoton ionization scheme using femtosecond visible pulses by Lux and co-worker. And it was the first demonstration that you can use multiphoton scheme to produce PECD. And one of the potential outcome of multiphoton PECD is the fact that you can use a coherent control scheme to basically maximize this chiral asymmetry in photoionization using interferences of multiple quantum pathways. And this is the work of the group of Christian Koch that theoretically demonstrated that using a finite manifold of 1+1 prime rampy pathways, which is interfering at the same final photoelectron energy, but by going through different intermediate Rydberg states, they can shape the pulse and try to optimize the chiral asymmetry in photoionization. And they showed that it can lead to more than a 5-fold enhancement of PECD compared to the single photon analog ending up at the same final state energy. So synthesizing such a pulse in the lab is very challenging for now, but it's interesting to know that this chiral asymmetry in photoionization can potentially be optimized using the standard coherent control scheme that we know in multiphoton ionization. And one very interesting extension of the 2+1 rampy PECD experiment of Lux and co-worker is going to the above threshold ionization regime. So again, the same group have demonstrated non-vanishing PECD on the first ATI peak, which shows that even ATI can be sensitive to the chirality of the molecular potential. So basically, sorry, I will. Okay, so yeah, at this point of the talk, we have seen that photoelectron circular dichroism can emerge in many different ionization regimes. So single photon, rampy, low order ATI. But as strong field physicists, one very intriguing question is how PECD will behave if we keep increasing the laser intensity and go towards the strong field ionization regime. And so indeed, so intuitively, as the laser field strength is increased, the sensitivity of the outgoing electron to the molecular potential is expected to decrease, and the trajectory of these outgoing electron is expected to be dominated by the laser field. And this is at the core of strong field approximation, which is often used in our field, and in which, in such an approximation, photoelectron is expected to be vanishing because the trajectory are not sensitive to the potential. And so this is why we decided to investigate the evolution of PECD when moving towards the strong field ionization regime. So to do that, we have looked at the ionization again of Fenchon using a relatively strong circularly polarized 800 nanometer pulse, so TISAF laser, in a regime where the Keldysh parameter is roughly 3. So still in multiphoton regime. And in this case, we can see that very high order ADI peak, which is extending up to the absorption of more than 10 photons. This is what you can see in the photoelectron angular distribution on the top. And looking at the associated photoelectron circular dichroism, we can see that there's a strong chiral asymmetry on all ATI peak, meaning that the chirality of the molecular potential is still imprinted on the electron trajectory, even in high order ADI regime. And to go one step further, what we have looked at is the photoionization of Fenchon using strong circularly polarized mid-infrared laser pulse to be in a regime where the Keldysh parameter is below 1. So in this case, 0.6. And here you can see in the angular distribution, so on the top, that the distribution is strongly peaked along the laser polarization plane. And this is like a characteristic that you enter the tunneling ionization regime let's say in an N-waving description. And you can see, looking at the maximum energy of these electrons, that you have absorbed a net number of photon of roughly 30, if you believe in this analogy of photons and strong field. And looking at the photoelectron circular dichroism, we can see much smaller. So before it was on the order of 10%, now it's on the order of 2%, so a much stronger, smaller, but non-vanishing photoelectron circular dichroism, which is a clear signature of the breakdown of the strong field approximation here. And so what we can conclude from these study is that the molecular potential is still able to imprint its chirality onto the outgoing electron wave packet, even being in the tunnel ionization regime, which is quite counterintuitive if you always think into the SFA type of picture. So these findings that I've just described have very strong consequences for our field. So indeed, it unlocks the possibility to use all the toolbox that we developed in strong field physics to study chiral photoionization. It also opens some question about the origin of PECD that I will try to talk about a bit later. So in the following, I will show you how we can use two-color phase lock Attosecond experiment to reveal a lot of different interesting dynamics in strong field ionization of chiral molecule. So the first experiment that I want to show is an experiment that we did here in Bordeaux. And so here we want to use the unique temporal resolution offered by Attosecond science. So in a way that people have used Attosecond spectroscopy to reveal the non-instantaneous nature of photoionization, as we saw in Francesca's talk this morning. And it has been shown, for example, that electron ejected from different molecular orbital or from different vibrational states, or also from different spin orbit splitted electronic states, are not ejected at the same time. So this is the question of delays in photoionization. And in the context of chiral photoionization, it seems natural to ask the question whether electron ejected forward or backward are ejected simultaneously, or is there a delay between them when you photoionize chiral molecule using circularly polarized light pulses. And to answer this question, we have used a two-color experimental setup, very similar in the idea of rabbit that I'm sure you heard about before in the week. But by changing the XUV, by replacing the XUV by a strong 400 nanometer circularly polarized light, and by using a weak 800 nanometer pulses to create these sidebands necessary for this measurement. And by scanning the attosecond delays between the circularly polarized 400 nanometer pulse and linear 800 nanometer pulse, we measure in a fully angularly resolved fashion, so using a VMI, the oscillation phase of the sideband for each emission angle in order to extract the ATI-induced ionization delay in chiral photoionization. And so what we did is we have extracted the forward-backward asymmetry in the oscillation phase and translate this in photoionization delay asymmetry for both enantiomers, so left and right end of camphor molecule. And on this plot, you can see the asymmetry of the ionization delay as a function of the ejection angle of the electron. So 0 degree meaning in the light polarization plane, and 90 degree meaning in the light propagation direction. So we can see that close to the polarization plane, so close to 0, where photoelectron circular dichroism is expected to be vanishing, the photoionization delays are also forward-backward symmetric, so asymmetry of 0. And when going towards light propagation direction, where the PECD is expected to maximize, the asymmetry of the photoionization delay reach a maximum value of roughly 25 attosecond, and which switch signs when we swap the molecular enantiomer. So the conclusion of this investigation is that in addition to a forward-backward asymmetry in the number of ejected electrons, there's also a forward-backward asymmetry in the temporal synchronization of the outgoing electron wave packet in chiral photoionization. And I think this is a very nice example to show how to use the strong field physics toolbox to learn about chiral photoionization. And one other important ingredient in our strong field physicist toolbox is the angular stretching of the photoelectron distribution when you use strong field ionization using elliptically polarized field. And this is often used in the context of Attoclock measurement. And so here the group of Frankfurt have recently investigated the influence of molecular chirality in such Attoclock-like setting. And by looking at the angle at which the photoelectron angular distribution maximize in the polarization plane, what they call phi max, as a function of the momentum coordinate along the light propagation direction, which is here PEX on your right, they have shown that the angular offset of the photoelectron distribution is forward-backward asymmetric, as you can show on the panel on your right. And basically, it means that the electrons are angularly stretched in the opposite direction if they are ejected forward or backward. And this offset angle is a new Chiral observable and can potentially be used to investigate strong field ionization dynamics of chiral molecule. And here I'm coming close to the end, so I want to show you another very important aspect in strong field physics, which is basically our ability to tailor the light field by using a combination of multiple color field with tunable polarization states. So for example, one of the very interesting field shape that one can generate is the one seen on your right, which you can synthesize using omega field and its orthogonally polarized second harmonic. So omega linear like this to omega like this, and the synthesized field look like the one on your right. And in the contrary to circularly polarized light, which is shown on your left, and which is as a constant helicity at every moment of this laser pulse, this tailored light field has an instantaneous chirality which switch signs every half cycles, as you can see on the figure. And it also means that this field has no net helicity. If you integrate over the entire pulse, this pulse has no net helicity. And but if you look on a subcycle level, it is chiral. And taking these characteristics into account, it is not so obvious if such a field will lead to photoelectron circular dichroism, or if the zero net helicity will lead to a forward-backward symmetric distribution. And by looking at this snapshot, which have been measured experimentally, one can see that photoionization with such a field lead to an enantiospecific forward-backward and up-down asymmetric photoelectron distribution, which means that the electron ionized from two consecutive half cycles of the laser show an opposite forward-backward asymmetry, and that the instantaneous chirality of the laser field is encoded in the final angular distribution of the light, of the electron, as well as its asymmetry. So the result from this slide, combined with all the results that I've shown in the last few slides, trigger an important question on the different role of tunneling and subsequent scattering of the electron in the potential in strong field chiral photoionization. And this will be my last example. And so if you want to disentangle tunneling and scattering, there was a beautiful paper a few years ago that explained us how to do that from a theoretical point of view. So, so basically by studying atomic strong field ionization using elliptically polarized light for a full Coulomb potential. So sorry, let me mention again something that I forgot. So this paper, the goal of this paper was to solve the debate concerning the origin of the angular offsets in attoclock measurement, to know if it's whether coming from tunneling time or scattering of the electron in the potential. And so they calculate this angular stretching for using elliptically polarized light with two different potential, a Coulomb potential and a Yukawa screen potential. And Torlina and co-worker have demonstrated a very clever strategy to answer this question with these two potential. So indeed, while the Coulomb potential capture the effect of both tunneling and scattering of the long-range tail of the potential, the Yukawa is only sensitive to tunneling because you screen this potential before the tunnel exit of the electron. And because the Yukawa potential is only sensitive to tunneling and it shows no angular offset, the conclusion of this work was that the angular offset in attoclock is mainly coming from scattering of the electron in the potential. And this was later on confirmed by experimental measurement by the group of Igor Litvinuk in Griffith in Australia. And so we used the same strategy. I'm done. It's the last slide. So we use the same strategy. So when I say we, I mean some theoretician in Bordeaux, so not me, myself. And so we study we did the same experiment, numerical experiment as Torlina, but for the most simple chiral molecule, H4 3+, which is a synthetic molecule that you can only study on your computer, which is known as the Bernardine in Bordeaux in honor to Bernard Pons. And basically, by using co-rotating circularly polarized light, omega to omega configuration, we look at the effect of going from a Coulomb to a Yukawa potential. And basically, in the Coulomb potential, you see both angular offset and photoelectron circular dichroism, while in Yukawa potential, you see no angular offset, a bit like in the work of Torlina, but you still see photoelectron circular dichroism. So this means the conclusion of this work is that just after tunneling, the chirality is encoded in the amplitude and the phase of the tunneling wave packet even prior to scatter in the potential. So this is an interesting perspective on the origin of chiral photoionization in strong field. So I had a few slides concerning application of PECD to measure enantiomeric excess, but I will skip it since I'm out of time. But hopefully we can discuss this in the roundtable session in the afternoon. And so just in conclusion, I hope that I convince you that photoelectron circular dichroism is an interesting phenomenon, and that now using the strong field physics toolbox, we can learn a lot about chiral photoionization. But flipping this idea around, we can also use very subtle effect in chiral photoionization to learn new things about strong field ionization, very subtle effects which are difficult to extract using photoionization of non-chiral targets. So this fundamental symmetry breaking of the interaction process can be used to investigate deeply the mechanism of strong field ionization. So with that, I want to thank all the collaborators from Bordeaux and also from other places. And also I want to thank you for listening to me for almost an hour now. Thank you very much.